Hello folks, welcome to the part 3 of our Building a Database from Scratch series. To implement everything I'm using Golang, but you can basically follow along in every language you use. For more context about the series and the materials that I use, please check out the short introduction video. This video will be a bit of theory. I believe it is important to see this in a dedicated video because this basically drives the design and the implementation more or less of the whole database engine. Next time when we implement the log manager, there will be code, I promise. If you remember from my last video where we implemented the file manager, the component that basically reads and writes data to disk, you know that the only way that the database engine can read a value from the disk is by reading a block that contains that value to a page of memory. And to write the value back to the disk is to write it to a page that is then flushed to the disk. Let's quickly see the diagram from the previous video. Okay. Here we have a file on disk, file F, that is basically an array of fixed sized blocks, essentially. And when a database engine wants to read some data that is located, let's say, in this third block, so 0, 1, 2, it will basically load the block into a page of memory, page P, and all of the data manipulation will happen basically here. And when the engine is done with manipulating it, it will be basically flushed back to that same block in the file. More or less straightforward. A database engine follows two important principles when it comes to moving the data between memory and the disk. These principles are to minimize disk access and to not rely on operating system virtual memory. Let's see this in a bit more detail. Like we mentioned, the first principle is to minimize disk access as much as possible. The reason for the importance of this principle can be nicely seen from this diagram. And I believe it is attributed to Jeff Dean from Google. And this picture in particular I took from Andy Pavlo, CMU database course. And in order to comprehend this even more, we can swap nanoseconds with seconds, and we will have something like this. Here you can see clearly what are the differences between all of these latencies. And you can see how much slower is the disk access compared to the memory access. So, and even with the fastest SSDs you can buy today, it is still orders of magnitude slower than the memory. Basically, because of what we see here, maybe the most important thing a database engine can do and try to do is to minimize disk access. And the only way to do this is basically to avoid accessing a disk multiple times for the same data, okay? And you might assume how we can accomplish this. It is with a standard solution to problems like this, essentially caching, okay? But it happens to be one of the hardest problems in computer science, right? It is cache or cache invalidation, and naming things, right? A database engine uses memory pages to cache disk blocks. By keeping track of which pages contain the contents of which blocks, the engine may be able to satisfy a client request by using an existing page and thereby avoid a disk read. Similarly, engine writes pages to the disk only when necessary. It basically tries to do as much changes to a page as possible with a single disk access. The need to minimize disk accesses is so important that it basically pervades the entire implementation of the database engine. For example, when an SQL query has several possible retrieval strategies, the SQL planner will choose the strategy that it thinks will require the fewest number of disk accesses. So this is our first principle. And the second one is don't rely on operating system virtual memory. This loading of a block from the disk and mapping it into a page of memory and creating this illusion that we have more memory that we actually do, to some of you maybe sound familiar. This is basically operating system virtual memory. Virtual memory is like a memory management technique that essentially abstracts away the physical memory from the processes that are running on the system. It allows a process to use more memory than is physically available on the system. And each process gets its own virtual memory space that is larger than physical memory space, all right? Memory, virtual and physical, is divided into fixed size blocks called, oddly enough, pages. Since not all virtual pages can fit into physical memory space, the operating system stores them on the disk in a swap file. When a process tries to access memory page not currently in RAM, a page swap occurs. When this happens, the operating system will first release some space in physical memory by storing some page to the disk, like last recently used page, and then load the requested page from the disk back into memory. We can talk a lot more about virtual memory, but in a nutshell, this is what it is. So when we go back to our database engine, and with this in mind, we could basically rely on the operating system mechanism and avoid essentially re-implementing everything, right? It could look something like this. So let's say we have a file F, that is on disk, okay? And this is our virtual memory space. Of course, we have disk blocks, and here we also have memory pages like this. But our physical memory is something like this. Okay, so this is RAM. And our database engine can say, okay, I need this whole file. It will be loaded to our virtual memory space. And like we see, the whole file will fit. But in terms of physical memory, it of course cannot fit, like we see here. But we don't care. We let the operating system do all of this mapping from RAM to disk and back and forth. So we are good, right? Of course, this is much easier to implement, but has a big problem for us, and that is exactly this. The operating system controls when the pages gets written to the disk, not the database. And there are basically three problems that arise from this. The first problem is transaction safety. Imagine you have an update query that will update data in multiple pages. The database engine needs to be sure that all those dirty pages are flushed to the disk atomically, okay? Operating system doesn't know what are the dirty pages in the context of the database, and it can flush them in any way it thinks is the best. But in the context of the database, it can be the worst. The second problem is crash recovery. Imagine if we crash in the middle of the transaction that is touching multiple pages. We cannot recover safely in that situation because we don't know what the operating system flushed and what is not. The database engine needs to know what is durable on the disk and what was lost in the memory during the crash. Okay. And also, there are times when the database needs to flush a page to the disk before proceeding with some operation. Usually, a write operation has to be written to the log that more or less always has to be durable, so we can do a crash recovery, okay? And if you rely on the operating system, this is simply not possible. This is related to write-ahead logging, and we will talk about it in the next video where we will implement the log manager. And the third problem is I/O stalls. Because the database basically doesn't know what page is in memory, we can have random I/O stalls whenever we want to touch something that is not in memory, okay? And this is particularly bad if we have a single-threaded database. Then in this case, everything will stall. Also, the operating system can flush a page to disk that the database will need at that time. And now we have a totally unnecessary swap happening, and again we wait for the OS to load the page back to the memory, and essentially that page was already there, right? Was already ready for us, but operating system flushed it. With all of this, we can see that relying on virtual memory will not only be horrible for the database performance, it is also wrong in terms of data durability and consistency. Essentially, the database cannot guarantee durability. To put it simply, relying on operating system virtual memory is really, really bad. Because of this, the database engine needs to manage its own pages in memory. it will allocate a relatively small number of pages that it knows will fit into a memory and that it knows it will need the most. And when a new block needs to be read into a page, the database engine and not the operating system will choose what page in memory to swap, okay? And it will first flush all of its contents back to disk, and only then it will load the requested block into memory. The component that handles all of this is commonly known as buffer pool or buffer pool manager. And we will actually implement it in one of the upcoming videos. Okay, folks, now that we know about these two principles, we can proceed with our next part, where we will implement the log manager that we briefly mentioned here. This is all for this video. I know there was no code in here, but I truly believe that it is important for us to understand these principles before proceeding with the implementation, and I really hope it was useful for you. Thank you for watching, and if you want to help me out, you could click on this like button and also maybe consider subscribing. See you in the next one. Bye bye.